Hi there, welcome to the second week of learning chemistry, higher chemistry from home. The first week we were covering some of the basics of the periodic table, talking about the bonding and structure there in the first 20 elements. So we were able to hopefully categorise by the end of that each of those 20 elements in terms of their bonding, whether that was covalent or metallic. You don't get ionic bonding in elements, and also in their structure, how they're arranged, whether they're arranged in molecules or networks or lattices. So we're pushing on this week and looking at trends in the periodic table. And the first of these, if we're just following the bright red book, is one that we're calling atomic size. Now, atomic size, like it suggests, is the size of an atom. But we measure it in terms of covalent radius, and there's a page in the data book that gives you values for covalent radius. That word, though, covalent radius, it actually comes from something quite specific, because if you're talking about the size of an atom, it's actually really difficult to measure. I'm going really old school here in my garage. I've got a chalkboard and chalk, but we're gonna have a wee think. And if you think about an atom like it is, right in the core, you've got a wee dense point of quite, the majority of the mass, the vast majority of the mass of the atom is there, concentrated in that core in the nucleus. And flying around that, you've got your electrons, okay? And we can kind of think of them as just really a fuzzy cloud, okay? The electrons, like we were seeing last week, okay, because on our journey of learning about the bonding and structure of the first 20 elements, we talked also about these things called London dispersion forces. They'll be coming up again and again. But the electrons, they're distributed randomly, they're flying all over the place. So it's actually really quite hard to say exactly where the atom starts and where the atom stops, because the electrons, which make up the furthest reaches of the atom, they're constantly moving. So it's very difficult to measure from there to there. Okay, so the measure is made by looking at an atom in a molecule. So if you've got one atom here and another atom up here, let's just keep it the same colours now, and if we have them covalently bonded together, now we know what a covalent bond is, we talked about this before, it's a shared pair of electrons. But if you think about what a molecule would actually look like, if you could actually zoom in and see a molecule, you'd essentially see two spheres kind of merged into each other like that. Okay, so now, because we've got two heavy fixed points, one there and one there, it's actually relatively easy to measure the distance between these 2 points. Okay, and if we take half of that distance, there to there, we call that the covalent radius. So you've got values in the data booklet that give you the covalent radius. Magically, that's them there. If you look at the far right hand side of the periodic table, you might just notice there's something not quite right. It doesn't look like our normal periodic table. There's something missing here. You've got your group 0 noble gases missing. That actually, when you think about it though, makes sense, because we've said from a long time ago that the noble gases don't make bonds. So it would be a bit surprising to find a covalent radius for something that doesn't make covalent bonds. So, covalent radius, we're interested though, next few lessons we're going to be talking about trends in the periodic table. And we're going to look at how it changes, how the trends vary along a period and down a group. So on the board I've got written, it's a bit hard to see, the lights kind of reflecting off it a bit awkwardly, but this is our second period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and we've got our electron arrangements of each of these. Now, if you were asked what would you predict as you're going along a period, well, you might well think, well, lithium, there's 3 protons, 4 neutrons, 3 electrons, okay? Beryllium's a bit bigger, you've got 4 protons, is it 5 neutrons, 4 electrons, so you're getting more of each thing as you're going on a period. And you might logically, just if intuitively think, oh well, they're going to get bigger and bigger and bigger and bigger. And that would be kind of sensible to think. But if you actually look at the figures, you find it actually gets smaller along a period. Beryllium is 134 picometers, Beryllium is a bit smaller at 129. Boron, carbon, nitrogen go 90, 77, 75, and 73, 75. So they're actually getting smaller. That means the atoms, as they go along a period, start off bigger, get smaller and smaller and smaller and smaller and smaller. And if you look at each period, it kind of does the same thing. Now, that, like I said, is a bit sort of counterintuitive. And the rationale that we have is saying, well, look at the electron arrangements. This is showing us that we've got 2 electrons in the first shell, 1 in the second shell. You're adding a second to the second shell, a third, a fourth, a fifth, all to the same second shell. So if you think about what that would be like, I've got sketched here a relatively big lithium and a relatively small fluorine here. So why is this? Why is this? How we account for this is by saying, well, that electron is getting cooled into the nucleus, just as these ones are, okay? But the nucleus here is 3 positive. There are 3 protons in a lithium nucleus. This one here though, fluorine, has got 9 protons. Its atomic number is 9. It's got 9 protons. So those 9 protons are pulling in more strongly. So as you're going along a period, as you add 1 more proton to each nucleus, that's giving the nucleus a stronger pull on those electrons. So they're getting pulled in tighter and tighter and tighter and tighter and tighter as we go along a period. And if you look at all the periods along the periodic table, you'll find there's the same sort of pattern. So next of all, we're going to rethink about groups. So we're going to look at group 1. We can actually just ignore hydrogen there because it doesn't really kind of belong in that sense. But if you look at the values for lithium, sodium, potassium, rubidium and cesium, those values increase as you go down the group. In other words, what's that saying is the covalent radius, the atomic size of these are getting bigger and bigger and bigger. This though is actually totally intuitive. It just totally makes sense. There's no kind of like deeper understanding that you have to have. It's just the simple idea. If you look, I've got the electron arrangements written out here. Lithium, 2 electrons in the first shell, 1 in the second shell. Sodium 281, potassium 288. Okay, you're getting more and more occupied shells. So then it kind of makes sense then that your atoms are going to get bigger and bigger and bigger and bigger as you go down the group. So you'll find that is the case. It holds for all the groups, okay, that we looked at group 1, but it's the same for any of the other groups. We could look at the halogens here in group 7, and you're seeing the same sort of idea. 71 for fluorine, 99 for chlorine, 114 for bromine. They just get bigger and bigger and bigger. And it's the same reason as you're going down each group, you're getting an extra shell of electrons added. You can refer back on page 8 in the data booklet. That will show you your electron arrangements, and sure enough, when you look at them, okay, going down, there's a bit of a scruffy old periodic table, this one, but going down you can see there each of them have got additional shells as you go down every group. So then, to sum up then, what were we seeing then? We were seeing this idea, first of all, what we're calling atomic size is really covalent radius. It's half the distance between 2 nuclei that are covalently bonded together. That was the first wee thing, the underlying thing. Okay, so what were the 2 trends we saw? As going along a group, we saw them getting smaller and smaller and smaller. And how did we account for that? We said that as you go along a period, you're getting more and more protons added to the nucleus. So that means you're going to get what we describe as an increasing nuclear charge along a period, which is pulling the electrons in closer. Down a group, the trend is that the atoms get bigger and bigger and bigger. And why is that? We're saying, well, we account for that because there are just more electron shells as you go down a group, more electron shells. So I hope that wasn't too rushed. There's plenty of additional reading that you could go and look at. I've put various bits and pieces in the resources folder.